Assalamualaikum warahmatullahi wabarakatuh. Today, our group want to present the studies about the MotoGP front winglet, which is include in external floor, design and analysis of mechanical part using CFD. So I want to introduce our members. First, Imran Hanif bin Abdul Rahim. Second, myself, Muhammad Farhan Akil bin Norazak. And third, Syamimi Fatihah binti Muhammad. So I want to continue through the introduction. So I will give the slide to Syamimi Fatihah.
Okay, so I will continue the first part, which is the introduction. As we all know, the MotoGP bikes normally strongly accelerate at 200 miles per hour or more than that. So the MotoGP will experience the basic aerodynamic drag, which is with the addition of acceleration can lead to instability or even the front wheel lift of the rider. So the winglet in MotoGP were inspired by the aerospace industry that we borrow from that industry to control the reduction of turbulence around the riders. And then the winglet that we used in the MotoGP function, same as the aerofoil in airplanes, in order to create lift. Meanwhile, in the MotoGP, it is the inverted airfoil that we use so that we can create the downforce. Okay, the last one is there are two major advantages of winglet, which is it is anti-wheelie at the high speed, and the winglet also give the grip to the front tire when braking.
So we continue to the problem statement. As we all know, since the racing field need the speed to win the competition, so the MotoGP are designed in all ways of specification to be able to compete in speed. The faster the speed of the MotoGP, the higher the probability to win the title. However, the current aero shape of the MotoGP has made some issue in the motor racing field, which is causing the MotoGP to wheelie when the speed is increased, and at the same time give trouble to the racer when they want to speed up. So the special winglet has been designed to add some downforce to the MotoGP in order to maintain steady during the racing. So the problem here is, what is the ultimate angle of attack that can give the optimum drag and downforce to the MotoGP. So
okay, now
stage.
Okay, thank you, Pak An. Farhan, sorry. Okay, now we're looking at the modeling stage. Okay, the chosen MotoGP winglet design for CFD fluid analysis is inspired by the 2019 Team LCR Honda Idemitsu bike. The figure shown in the next slide, it utilized an open wing design, specifically cantilever wing, which is defined as a wing that uses no external strut for bracing. All support is obtained from the wing itself, and the wing spars are built in such a way that they carry all the torsion and bending loads. The winglet part was designed in CATIA V5 in generative shape design workbench to follow the real life scale as close as possible and according to the MotoGP regulation, in which the maximum length allowed is 600 millimeters. Okay, next slide please. Okay, as you can see in the slide is the LCR Honda Idemitsu bike and also the CAD drawing of our winglet design. Okay, next slide. Now, okay, the assembly of the CAD drawing or the winglet consists of mounting surface for the front fairing of the bike, and also the cantilever wing on the right and left side. For analysis purposes, there are 6 angle of attack variation for the winglet, which are 2.5 degrees angle of attack, 5.0 degrees, 7.5 degrees, 10 degrees, 12.5 degrees, and 15 degrees. The angle of attack is incremental of 2.5 degrees. Okay, so the angle of attack was measured at the neutral line of the winglet. The winglet is when the design was done in the kaca, it is imported to the geometric tab in the ANSYS fluid flow fluent analysis system workbench in IGS format. One thing that we face problem here, actually we can import directly the CAD part to the geometry tab, but it seems that we cannot import the CAD part. Instead, we use IGS format. Okay. Inside the geometry tab, there are 2 workbench, which is the space claim and also design modeler. We use space claim to define or improve the part CAD drawing because our CAD drawing is consisting of multiple joints and surfaces. So we use space claim to combine all the surfaces into one solid. So once that is done, we move on to design modeler, in which we prepare the improved part, the solid, for CFD fluent analysis. In this workbench, in this design modeler workbench, we rotate the winglet to the desired angle, and then we create an enclosure around the winglet. Okay. So the next part is meshing. Next slide, please, Van. Okay. In the meshing stage, the meshing workbench was launched from the CFD Fluent Analysis System workbench by right-clicking on the mesh tab. Okay, so you can see the symbol there. In meshing workbench, click on the mesh tree, and then the configuration was set up as follow, while other selection was kept default. So you can see the details of mesh. We changed the element order from linear to quadratic, and also the element size of 10 mm. Okay, once that's done, mesh was generated and workbench was exited. Next slide, please. Okay. So now we're moving on to Fluent CFD workbench. The setup workbench was launched and loaded. And to make setting up easy and clearer, the wall faces were hidden, exposing only inlet, outlet, and also the solid, the winglet part. On the left setup tree, viscous model was set to SST K omega, and materials were also checked for fluid, which is air, as the analysis medium. Other than that, it is not important. Under the boundary condition tree, inlet was specified to velocity inlet type with velocity of 44.44 millimeter per second. 44.44 meter per second is equivalent to 160 kilometer per hour, which is the average speed of MotoGP bike racing in the circuit. And then the outlet was specified to pressure outlet type with gauge pressure of 0, and wall was checked for wall type. Under reference value, the compute from inlet was selected, and the surface area of the solid was keyed in, which is 0.23131 meter square. This surface area, you can find it in the design modeler. Select the solid, and it would, in the detail on the left bottom will show how much the surface area of our solid. Okay, so on the left solution tree, method configuration as shown in the next figure. And also under control, the flow current number was reduced from 200 to 100 count only. Okay, next slide. Okay, so as you can see, this is the method, I believe so, method configuration for the Fluent CFD. Okay, once that's done, I will move on to the next slide. Okay, so under report definition, we want to set up the desired force or coefficient that we want to obtain. So in this Fluent CFD analysis, we desire drag coefficient, lift coefficient, drag force, and lift force. So in the Fluent CFD, there are no downforce coefficient and downforce coefficient. Basically, lift and downforce is just the same thing. It's just reverse inverted in direction. So, and also the force vector were adjusted accordingly to the direction of the solid and in which axis it located. Once done, the calculation was initialized under initialization with hybrid initialization selected. And finally, the calculation was proceeded under the run calculation tab with 500 number of iterations. This once the calculation is completed, we can obtain the values of forces and coefficient. Okay, and once that's done, the values were tabulated, the result, and we exit the CFD workbench. Okay, then we enter the post-CFD fluent analysis, which is the result in the workbench, in the analysis system workbench. So the post-CFD workbench was launched by clicking edit on the results tab in the analysis system workbench. And then plane one was created under the location drop-down menu, and the X plane was selected. The Y value for the plane was adjusted so that the plane lies in the middle of the wing and applied. Okay, next slide please, right? Okay. Once we created the plane, we can create our contour plot by selecting it on the top left menu. So the plane one that was created earlier was selected as the locations. Pressure was selected as the variable, and the number of contours was set to 500 and then applied. Then we will obtain our contour plot and save the plot. Okay. For velocity plot, the variable was changed to velocity, and also the same procedure applied, and we save the plot. Okay. Okay, we'll be moving on to results. I'm passing the presentation to Shamimi. Please, Shamimi.
Okay, thank you, Imran. Okay, so after we do all the steps, as Imran mentioned it before, this is the result that we obtain from the ANSYS analysis, and the right that is the graph and value of the drag force and the force inside the graph. So at the graph also, the x-axis is the angle of attack and the y-axis is the forces. And the yellow line in the graph represent the lift force versus angle of attack, while the orange line is represent the drag force versus angle of attack. And then we back to the table. That is the ratio of the lift force over drag force. The ratio shown in the ratio is like the the ratio shown is the ratio of the lift over the drag force. So when the higher the ratio is represent how much the downforce outweigh the drag force. So in the MotoGP bikes, we need the maximum downforce and the minimum drag force. So I will pass the presentation to Pak An. Farhan, I'm sorry.
Thank you, Shamim Fatihah. So for the discussion, as based on the results obtained, okay, it shows that the angles of attack play a big role to give the most optimum drag force and lift force. But in MotoGP concept, it is inverted to downforce. And the downforce lift force ratio determines the best design. According to the ratio, an angle of 7.5% is the best angle due to the higher ratio value. Logically, in the physics concept, the angle influences the fluid's velocity that flows through it. Bernoulli's principle states that an increase in the speed of the fluid occurs simultaneously with a decrease in static pressure or a decrease in the fluid's potential energy. The decrease in static pressure causes the unbalanced pressure condition in both sides of a fall shape, and at the same time it makes the net force, which is the drag and lift force. So we are at the end of the presentation. So the conclusion is the winglet technology is very useful in the racing field. The winglet with the bigger angle of attack is more preferable to ensure the downforce is bigger enough to maintain the front wheel instability. As investigated, the angle of 7.5 degree is the best angle of attack that produces the drag and downforce that is suitable to the MotoGP. So that's all from us. Thank you.
Thank you guys. Thank you, Doctor.